In today's episode, I will explain how SVM support vector machine algorithm works. We will discuss its basic principles and then implement it from scratch in Python. Finally, we will use it to classify 2D data by dividing it into two categories. Let's get started. The SVM support vector machine is supervised machine learning method used for classification. The main goal of SVM is to find hyperplane that maximally separates different data classes while minimizing classification error. However, it cannot be just any separating hyperplane. It must maximize the distance to nearest point of each class, which we will later refer as margins. Imagine two groups of points on a plane belonging to two different categories. The points in one group are more similar to each other than they are to the points in other group. In other words, they lie closer to each other in the feature space, which in our example is limited to two dimensions represented by x and y axis. Our goal is to classify new points whose categories we don't know. But how we can do it? For linearly separable data, we can separate them using a hyperplane, which in our two-dimensional case takes the form of straight line with the equation a times x plus b times y plus c equals 0. Data on one side of the line will be classified into one category, while those on the other side will belong to the second category. In a 3D space, a hyperplane takes a form of flat plane. Unfortunately, I can't visualize higher dimensions, but the mathematical representation of these equations remains consistent. In n-dimensional space, the general equation of such a hyperplane can be represented where the coefficients form a weight vector w and the coordinates of points are represented by vector x. B is a bias that shifts the plane relative to origin. Translating this general equation back to our 2D example, the components reduce to the form shown on the screen. Returning to our problem, there can be many lines that correctly separate our two sets of points. Which one is the best, and how do we choose it? In SVM, the goal is to find a line that is far as possible from the nearest points in each class. In other words, we want to determine two parallel lines equally distant from the decision boundary passing through the nearest point in each class, while maximizing the distance between them. This line defines the margins, and the nearest points are called support vectors. The margin lines are parallel, so their weights vector w is the same as that of the decision boundary. We set the bias so that the difference between the two margins line is 1. This choice is arbitrary, but it simplifies calculation by ensuring that the SVM algorithm will scale itself to the data during training. Now let's focus on how the separating plane and its margins are found. The optimal solution is achieved by minimizing the objective function, which consists of two parts. The first part minimizes the length of the weight vector, which is inversely proportional to the width of the margins. The second part is the hinge loss function, which penalizes misclassification or points lying within the margins. By minimizing the weight vector w, we maximize the margins. If we want to calculate the distance between two parallel lines, we use the following formula. Parallel lines have the same weight vector, but differ by the bias term. For margin equations, a simple transformation shows that the distance between the margins is inversely proportional to the norm of weight vector w. To maximize the margin, we need to minimize the length of the weight vector. The second component of the objective function is the sum of the hinge loss values for all points. It equals to 0 for points correctly classified and located outside the margins, and it's positive for the misclassified points or those within the margins. Plugging data into the equation of the separating line results in positive values for the points above the plane and negative values for the points below. The condition of correct classification of a point outside the margins can be expressed as a simple formula. We will minimize the objective function using gradient descent. We need the partial derivatives with respect to w and b. Depending on whether the point lies outside the margin, the weights and the bias will be updated differently. Before we move to code editor, it's important to mention that the solution we will implement doesn't work for all cases. For non-linearly separable data, we use the technique called the kernel trick, which transforms the data into higher dimensional space where it can be linearly separated by hyperplane. However, discussing this method goes beyond the scope of this episode. So let's now focus on implementing SVM algorithm for linearly separable data. Before jumping into the code, we import the necessary libraries. We will use NumPy for handling data, make blobs to generate the test data, matplotlib for visualization, and SVM from scikit-learn for comparison. The first step is to generate the sample data for classification. We use makeBlobs to create two clusters of points with different centers. Then we convert the labels to -1 and +1 as required by the SVM algorithm. Next, we plot our data to visualize their spatial distribution. We use color to distinguish the two classes, blue for +1 and red for -1. The visualization helps us understand how SVM will separate this data. Additionally, if we have calculated weight and bias, we can plot the decision boundary and margins. Now we will implement SVM algorithm from scratch. Our implementation will focus on minimizing the cost function, which aims to separate the classes as efficiently as possible. We begin with defining the SVM class and initializing parameters such as learning rate, regulation parameter lambda, and number of iteration. These parameters control the training process. The init constructor will set initial values. We also initialize the weight and bias as none. In fit method, we first calculate the number of samples and number of features in the dataset. Then we initialize the weights vector as a 0 vector with the size equal to the number of features, and the bias is set to 0. The weights will be later updated during the training process to optimally separate the classes. The for loop iterates over the data, updating the weights and bias. The condition checks if the sample satisfies the margin condition, meaning whether it is correctly classified and lies at a sufficient distance from the decision boundary. Depending on whether the margin condition is met, the algorithm updates the weights and bias. If condition is true, meaning the point lies outside the margin and the weights are only updated based on regularization. This helps prevent overfitting. However, if the margin condition is not met, meaning the point lies within the margin or is misclassified, both the weight and bias are updating using the hinge loss function. The hinge loss penalizes points that are too close to the margin or are misclassified, which helps adjust the decision boundary. The final part is the predict method, which classifies new data. We use the np.dot function to calculate the result. The result is the dot product of the weights and features plus the bias. Then we use np-sign function to assign the class label -1 or 1 based on this result. Now we create an object of our model and call fit method to train the model on the data x and y. We use the previously defined parameters, learning rate, lambda param, and the number of iterations to control the training process. After training the model, we make prediction on the training data. The predict function returns predicted label -1 or 1 based on the weights and bias calculated by the model. Next, we calculate the model's accuracy by comparing the prediction label with the actual values. The np-min function returns the percentage of correct classifications. Finally, we display the result using the print function and call the plots SVM function to visualize the data, decision boundary, and margins. This helps us see how well the model separates the two classes. Now we will compare our custom SVM implementation with the model available in a scikit-learn library. Similar to before, we create the model object and train it using fit method on the same data x and y. We use a linear kernel since we are considering linearly separable problem. Without going into too much technical details, this kernel parameter allows us to apply so-called kernel trick, which is used when the data is not linearly separable. In today's episode, we are focusing only on linear cases, but the kernel trick enables SVM to handle more complex cases, which we will cover in future episode. As you can see, the scikit-learn model is much more optimized and achieves high accuracy in less time. Finally, we visualize the data and decision boundary. And that's it for today. In this episode, we implemented a simple SVM algorithm for linearly separable data and compare it with the scikit-learn model. Remember, our model is a basic version. Next time, we might dive into more advanced technique like a kernel trick, which handles nonlinear data. If you want more content like this, don't forget to leave a like and subscribe to the channel. Thanks for watching and see you in the next episode.